Wei-jie very well. Wei-jie did his PhD in Beijing with Yuxin Liu. Actually, what I didn't know is that he was an undergraduate in Dalian. So essentially, you're going full circle back to Dalian. And after his PhD in a short postdoc period in Beijing, he went to Brandon University in Canada, working with Maggie Carrington. And from there, he got a prestigious Humboldt Fellowship and went to Heidelberg. So when he contacted me about going to Heidelberg, I was very happy to act as a host, because I was already very impressed by his achievements, in particular concerning QCD at finite temperature and density, and also formal developments of functional methods. And when he was in Heidelberg, we started the collaboration. So that was really collaboration on equal terms on the phase structure of QCD. And I think he's one of the chief proponents for doing phase structure studies with functional methods in QCD. And we have a shared publication on this together with Fabian Rennecke, and I think I don't tell too much that I'm very happy to be on this paper. And Wei-jie and Fabian run the show. And from then on, in particular with his group in Dalian, he did many nice works together with me and alone. So again, I take this opportunity to thank you for this very nice collaboration. And it's your show now.
Okay, thank you, Yang, for the introduction. So I share my screen. Yeah. Okay. Okay, so can you see my screen?
Yes.
Okay. And thank you for the introduction. And first of all, I would like to thank the organizer for inviting me to give a talk in this seminar. And in this talk, I would like to present some recent progress in the studies of the QCD at finite temperature and density within the functional renormalization group approach. And I also would like to take this opportunity to thank the members of the FQCD's collaboration for collaborating on some subject. Oh. Okay, this is a sketch of the QCD phase diagrams by Fabian. And in these regions, the small chemical zero and small chemical potentials, it's very low that there is a continuous crossovers about 115 MeV. And but at the regions of high densities, because of difficulties both in the theoretic calculation and experiment, and we lost quite a few there. And but it's conjectured or argue that there is a first orders phase transition. So if that's true, there must be a endpoint of this first orders phase transition line. Here just denoted by the white dot. And in this critical endpoint, this is a second orders phase transition point. And there, the correlation, not only the correlation length is divergent in the thermodynamic limit, but also the realization time, is also go to infinity. And this is also called the critical slowdown. And this is very easy to understand from the potentials and the potential of water as the functions of water parameters. And we can see when the temperature is below or larger than Tc, the curvature here is non-zero. And we can say when it will take a finite time for the small ball to roll down to the equilibrium position. But in the case when the temperature is close to the critical ending point, the potential is very flat, and the curvature here is 0. So from this plot, we can see that it will take infinity times for the small ball to roll down to the equilibrium position. And this critical slow, this relaxation times is dependent on the correlations through powers functions. And the orders of powers is just described by the dynamics critical exponent. Here is denoted by the Z. So so we conclude that in order to study the QCD phase structures related physics, we need a nonperturbative approach. And in this approach, the errors at the finite density is controllable. And if in this approach, we can deal with the real-time dynamics, that will be very useful. And recently, the STAR collaborations that report there's measurement of the skewness and kurtosis of latent protons distributions in the beam energy scans experiment. And it's found that along monotonic behaviors of kurtosis at the functions of colliding energy is found. So does that means we have, does that these long monotonicities of kurtosis means that we have entered into the critical regions, or in other words, can we use the theoretical calculation and also the experimental measurement to pin down the location of a critical endpoint? And in this talk, I will discuss it. Okay, so this is the outlines of my talk. In the beginning, I have gave a very short introductions, and in the following, I will give a brief reviews about the functional renormalization group or the renormalization group. And then I will present some FRG's result for the QCD and finite temperatures and density. And if I have time, I will discuss a bit the FRG in the real-time formalism. And finally, I will give a summaries and also outlook. Okay. In the FRG's approach, we introduce infrared regulators for the functional, the generating the function. That is the regulator. And for these regulators, we can see that when the momentum is smaller than the RHIC scale K, the regulator is finite. And when the momentum is larger than K, it will go to 0 very quickly. So in the, and through the regulators, we can see that the quantum fluctuations of a momentum is smaller than K is suppressed, but the fluctuations of high momentums are not suppressed. So from these, we can get the flow of Schwinger functions and given by this. And after a Landreau's transformation, we can get the flow equations for the effective actions. So with this flow equation, when we integrate the RHIC scale here, denoted by K, from a very high UV cutoff to the infrared limit, K is to 0, and quantum and thermal and densities fluctuations of different momentums are integrated in successfully. And so when the RHIC scales is to in the infrared limit of a full quantum series is obtained. Okay. I would like to discuss about the chiral symmetry breaking in the languages of the renormalization group. And in this plot, I show a typical beta functions of the 4-quark couplings. This is the beta function is just given by these equations, and we can see this beta functions is just given. It can be obtained by the flows of a 4-quark coupling, and given by this equation. And this first terms is just come from the dimensionals of 4-quark couplings, and the other 3 terms correspond to the 3 diagrams, and these ones just correspond to the 2 4-quark couplings, and this is just the 1 4-quark and the 1 gluon exchange, and this one correspond to the 2 gluon exchange. First of all, I focus on the case when the strong couplings G here, G is just 0. And this is given by the black line. And from this plot, we can see that this is this point, the orange point, is just a infrared fixed point. And this one is the UV fixed point. If we give an initial value for the 4 coupling, which is just here, for example, here, it's smaller than the critical value. With the decrease of the RHIC scale, we can see it will go in this way, and will be decreased. So there is no chiral symmetry breaking, and there is no quark mass productions. But if we give an initial value of the 4-quark couplings is larger than these critical values, we can see it will go in this way, and it will increase. So that will cause the chiral symmetry breaking and the quark mass production, and that is correspond to this line. If we just turn on the temperature, just given by this dashed line, the UV fixed point will move on the right. We can see if it located this case, when the temperature increase, it will become from this case to this case, from this case. That means the broken chiral symmetry is restored with the increase of the temperature. If we turn on the strong coupling, that means that here the G is non-zero. We can see the global curves will move downward, and when the strong coupling is larger than critical value, for example, the GC here, so the entire curves will be below the x-axis. That means whatever, no matter what the values of the initial values of strong coupling, it will go to infinity. That means the chiral symmetry breaking is always happen. Okay, so if we couple the flows of the 4-quark couplings with the flows of the inverse quark propagator, we can study the mass productions in in terms of RHIC scale, renormalization group. And this is the flow diagrams in the planes of dimensionless quark mass and the dimensionless four quark coupling. And we can see here, this point just corresponds to the UV's fixed point. And in this part, we can see the critical point just developed as a critical line. This red line, this given by this red line. And here we can choose several selective evolution trajectory. And here in these two plots, for example, the red lines corresponding in this region, and the blue lines corresponding to this region. They just correspond to different values of initial strong coupling. And we can see in this region, these two lines is as functions of K with the decrease of K, the mass is still very small in comparison to the blue one. And also, this also happens for the four quark coupling. We can see these two values are also very smaller than these two. And you can see this y-axis is log scale. That is, that means on the left-hand side of the critical lines, there is a few chiral symmetry breakings, and on the right-hand side, there are significant chiral symmetry breaking, and a lot of dynamics quark mass is generated. And also, in these regions, there is a characteristic that we can see this line, the strong couplings go up very quickly and then decrease. And in this part, we show the four quark couplings of the tens fields complete channel. And this blue lines is just correspond to the scalar and Schroeder scalar channels, and in the two flavor, this is a sigma and pi, and others correspond to, for example, the vectors and the actual vector, and some others will say eta or a, and we can see in the vacuum, the four strong couplings is dominated by the scalar and Schroeder scalar channel. So this slide tells us that the flows of the two quark inverse, the flows of the quark propagator, together with the flows of the four quark coupling, playing the same roles as the gap equation. So that we are responsible for the quark mass production. Okay. The renormalization is also very suited for the descriptions of bound state. And usually the bound states are encoded in the endpoint correlation function. Here we can take the meson, for example. That is the four quark vortex. When the total momentums of a quark and the anti-quark, here denoted by the P. When the P is in the Minkowski space and it's close to the unshared pole mass of the meson, this four quark vortex can be described or approximated by two quark and mesons couplings collected by a mesons propagator. And this one just correspond to the beta sub theta amplitude. And here, this process, if we use one channel approximation, these equations can be described by this flow equation for the four quark couplings of the pion channels, like this. This is P square. And if we just neglect the last terms for the moment, we can solve this flow equation analytically the solutions given by this equation. And so we can see that the pion mass is just can be determined by the zeros of the denominator here. So this and one can see. So this is 0, and this is the 4 quark coupling is divergent. So in this plot, we should just this 1 over lambda as functions of p squared. And we can see in this region, and these different curves correspond to the different values of the quark mass at the UV cutoff. That is, which can be regarded as a constant quark mass. And in these regions, just on the right-hand side of there's vertical lines. That is the Euclidean space, and on the left-hand side is just the Minkowski space. And one can see is the pion mass just can be determined from the position of these curves across these so y is the zeros line. And in this plot, we show the determined pion mass as the functions of the constant quark mass. And we can see when the constant quark mass is equal to 0, the pion mass is also vanished as well. That indicates that the Goldstone series is also guaranteed in the RHIC flow. So that means in our calculation, the chiral symmetry is kept. Okay, another way to include the composite or mathematics degrees of freedom is to use the method, which is usually called the dynamics hadronization. That is the method that, for example, we introduce RHIC scales composite fit, that just be the phi, and that is dependent on the RHIC scale k. And the phi, these phi's is just the original field in the QCD, the gluon and the ghost and the quark. And we introduce that the expectation values of a partial T, the phi is proportional to, for example, the bilinear quark field and also the bosonic field. And this is what you want to bosonize. And after that, the Wetterich equation is modified as this, and these other two terms is come from the dynamics hadronization. And in this case, we can get the flow equation for the quark couplings just like this. This is A dot, it's just the hadronization functions. This is the flows of for quark, and we can choose the 4 quark couplings is identical to 0 for every value of k. That means that we are in fact do something like that. They do the Hubbard-Stanovich transformation for every value of the k, right? And this we can get the hadronization function A dot here. And this will go into the Yukawa's flow. So in this way, we can just to include the 4 quark interactions in the Yukawa coupling, just like this. And in the last slide, that is also playing the same role, right? And after that, we can get the flow equation for the effective actions. It received a contribution from the gluon, and that is ghost, and this is quark, and this is the composite field. And in our case, that is the most important, just the pion and the sigma. And so with this approach, there's no double counting. And in this plot, I show the Yukawa couplings at the functions of the RHIC scale k. We can say these different curves correspond to different values of the temperatures. At here, the calculation is performed at the vanished chemical potentials, and we can see the effect of temperatures. It just play a role in the regions of a low scale, and in this part we show the effect is full quark coupling. This H bar and over by pi square. That is the effective full quark couplings at the functions of K for different value of the temperature. Okay, in this slide, I would like to show how the low energy effect theories emerged laterally from the original QCD. Here we show this plot. This plot just shows the black ones denote the strong coupling, and the solid is the light quark gluon coupling, and this dashed line is just the strange quark gluon coupling, and the red ones correspond to the Yukawa coupling, and we can see in the high energy scale. When the K is very large in the perturbative regions, the strong couplings is play a dominant role. But when the scales is lower down to about, here is about 600 or 800 MeV, we can see the red lines is above these black ones. And I should remind that this is also a log scale. So that means the composite or mesonic degrees of freedom take over the active degree dynamics from the particles ones when the RHIC scales is in the RHIC scales in the low energy region, right? And in the right plot, we show the propagator's gapping. And also this is the black ones is for the quark. This is light quark and this strange quark. And this red lines is just correspond to the meson. And once more, we say that in the low energy scale, the mesonic degrees is larger than the quark propagators. And so in this calculation, we show that the low energy effect theory is emerging laterally from the fundamental theories in the regions of low energy, which is in good agreement with the viewpoint of the renormalization group. Okay, here in this slide, I choose the truncation scheme, which we used for the correlation function, and perform the derivatives with respect to the different fields. We can get the flow equation for the correlation function. For example, for the propagator, this is quark and this is gluon and meson. And also, we can also get the flow equation for the 3-point function. This is the quark gluon's vertex and the 3 gluon vertex, and this Yukawa coupling. And from this flow equation, you can see these 2-point correlation functions is also dependent on the higher order one. For example, this is a 3-point, this 4-point, and this also. So we, in our calculation, if we want to do some real calculations, we have to do the truncation. We use the vertex expansion. What is the vertex expansion? It just means that we truncate, for example, to the 3-point vertex or 4-point vertex. But this truncation is guaranteed by the apparent convergence. The apparent convergence is just, for example, when we include more higher orders vertex in our calculation, the result is stable. And in the following, so we'll show that the calculated results are indeed stable. And also, we also expand the flow around the two flavors gluon propagator in the vacuum and include, for example, the strange products contributions and also the the effect of the finite temperature and the densities through the flow. And also very recently, the effect is mesonic potential. The two flavor is improved to the full potential of 2+1 flavor. And here in this plot, we show our calculated the strong coupling, the running of strong coupling. These different color correspond to the light quark gluons coupling, and these strange quarks gluons couplings, and the blue ones just denote the Schwinger gluon coupling. And we can see in the perturbative regions, they agree with each other, and also the in good agreement with the perturbative prediction calculate result. Okay, here I show the calculated result for the gluon tracing function, and in the vacuum at the 0 temperature, so and in this plot for the finite temperatures, and here I will show the gluon tracing functions. This one, the red ones for the two flavor, and the black one is for the black one is for the 2+1 flavor, and we compare our calculations with the lattice result. We can see the agreement is very well. And for the finite temperatures gluon tracings, we can see our result is also comparable to the lattice result. Okay, here I introduce the parameters in our calculation, and for the QCDs here, the parameters is determined at a large momentum scale. For example, here we take the lambda, this UV cutoff. For example, we choose 20 GeV, but this theory, you can vary the values of lambda because the series is RG invariant. The final result will not dependent on the scales what you choose, only if you choose the lambda is large enough, right? And so after that, the parameters is just for the two flavors QCD. The parameters is just given by the strong coupling at the UV cutoff, and also the U quark and D quark current quark mass, or the light quark at the UV cutoff, but that is determined by the pile mass, right? And for the 2+1 flavor QCD, besides the strong coupling and also the light quark coupling, there is also a strange quark coupling, a strange quark mass at the UV cutoff. But that is determined by the ratio between the strange quark constant mass and the light quark constant mass. That is determined by 27. And after that, we find that the K mass is about 500 MeV. That is agreement with the experimental measurement of the K mass, right? Here I show some calculated result. That is a renormalized light quark condensate. This is the quark condensate is just given by the trace of a propagator, and we normalize it by subtracting the condensate in the vacuum, and the black lines is our result, and we compare the lattice result, and note that this is the result is obtained in our lightning papers. And very recently, so as I have mentioned, we improved the truncation for the sector of the strange quark, and also to improve the mesotic potential to the 2+1 flavor. And we can see the new result here. It's very stable. It's very stable. It's also in good agreement with the lattice result. And in this plot, we show the renormalized light clock as functions of T for different values of baryon chemical potential. And from the position of the infection point, here just as a position, we can determine the pseudo's critical temperature for the chiral symmetry for the chiral phase transition. And in this slide, we show some others observable. This is a reduced condensate. That is just given by the difference between the light quark condensate and the strange quark condensate. And this result shows the in the mu b 0 and as functions of T. This is also obtains our 19th paper. And and also, so very recently, our calculated reduced condensate is also very stable. And we can see that our truncation, as I have mentioned before, our truncation is converged. And in this plot, we show the effective 4 quark couplings as functions of T for different values of mu b. Okay, we show the result for the curvatures of our phase boundary. The curvatures of a phase boundary is just determined like in this equation. Here, this is the pseudo-critical temperatures at a finite mu b. We expanded in terms of a mu b square. And the curvatures just correspond to the coefficient of the leading water's contribution. And this quantity is very important. It's a very key quantity. And we can see that for our calculation, for the 2+1 flavor and these 2 flavors, this value is consistent with the lattice, these 2 lattice groups result. And in this plot, we show that these two in this plot, we also show 2 results from the Dyson-Schwinger calculation in about 20th and 15th. We can see these two, for these 2 phase boundary, the curvature is obviously larger than the lattice result. So, oh, sorry. And so I choose the estimate for the location of a critical endpoint from functional QCD. And for the FRG calculation, we show that the T and mu b is a critical endpoint is given by this value. And for the Dyson-Schwinger calculation, this one is from Fei and Young, and this one is from the Chris Young and his collaborator. We can see these 2, if we plot these 3 critical endpoint in the first diagram, it's just to give this in this region. We can see these they estimate the critical endpoint converging in a very small region. And also, I also would like to list several take-home message. There is no critical endpoint observed in mu b over T is smaller than 2 or 3 from lattice calculation, right? And recent studies of a QCD phase structure from both FRG and Dyson-Schwinger have shown convergent estimate for the location of the critical endpoint. But I should remind that consider the relative larger azoles beyond this line, mu b over T is larger than the 4 from the functional method. so we can arrive at reasonable estimations for the region of the critical endpoints that is approximately larger than the 415 MeV and smaller than 615 MeV. And also and in this plot, we also show the update for the critical endpoint from the functional calculation. And this is the update from the FRG. And I have mentioned that we improved the truncation for the sector strange quark and the full mesons potential. And this is just to move from the black to the red one. So that is also very stable. And also from the Dyson-Schwinger calculation and from Fries, Correlates, and Young, and they include the thermal splittings for the correlation functions at finite temperatures, and it's found that the effect of thermal splittings on the locations is of CEP is very small. And this is the values, the approximate values for the gate. That is also it's very close here. It's 110 and 600 MeV. And but I should remind that. Oh yeah. I should remind that the state of art functional calculation have passed through the latest benchmark test at the vanished was most baryon chemical potential. That is guaranteed by the curvature, right? And another thing is that the region of reliability of the kind of best truncation is we can make a crude or approximate estimate. It's just the below that is smaller than the mu b over t is 4, and beyond these lines, the truncation errors increase rapidly. So in this case, sorry. So we don't say that we have a prediction for the, that is the reason why we don't say that we have a prediction for the location of the critical endpoint. That is because in this region, the errors is big, right? And we also investigate the critical temperatures in the chiral limit and the magnetic equation state. And this is the susceptibilities at the functions of T for different values of a pion on mass. And from this positional peak, we can determine the pseudo critical temperatures. And here we show the pseudo critical temperature at the functions of the pion mass. And the black ones is obtained from FRG. And we also compare our result with the latest result that's given by this red and yellows, and also this green point. And recently, the Dyson-Schwinger result from Frey and Young is also shown here. We can see the FRG's result and the Dyson-Schwinger's result is consistent with each other. And the critical temperature from the latest result is about 113, and but our FRG and Dyson-Schwinger's result is relatively larger, and we can see the ratio. These lines for the FRG and the Dyson-Schwinger is smaller than the latest calculation. And another thing is that we also show investigate the critical region. We choose the critical is Poland delta 1/delta as the functions of the pound mass. We can see when the pound mass is very small, that is a correct value about 1/5. This region is very small, and when we increase the pound mass, is go up and also go down. This is calculated from the low energy effect theory, but this behavior is recently confirmed by our first principles QCD calculation. And recently in Fries and Young's recent papers, they show a very interesting plot. That is in the place of the temperatures and the constant clock mass, and they show the water parameter, chiral condensate as the functions of the H. And we can see these red parts, they just correspond to the very small critical region, and this is the green regions correspond to these terms 1/5, just correspond here to dominate, and the blue ones is dominated by the 1/3 terms, and this green regions is just dominated by the constant clock effect. In our recent calculation, we also obtained the equation of the state at a finite mu b and found our FRG's calculation. This is pressures as the functions of mu b and also the 3D plot. And this is the temperature. This is pressure. This is the entropy, and this is the Baryon number densities, and this is the energy density, and this is trace anomaly. And we calculated to, and in this equation state, the the effect of critical endpoint is included naturally. And we also, our calculation law is performed up to mu b, so about 600 MeV. Also, so we calculate the Baryon numbers fluctuations in the low energy effect theory, and this is the 4th water, and this is half water, the 6th water, and this is 8th water, it's the 10th water, and we also compares our result. That is the mu b is 0. We compares our calculation with the lattice result, and we find that agreement it's very well. And in our calculation, we can calculate the Baryon number density, Baryon numbers fluctuation at a finite mu b directly. That is the full calculation. We can also perform the ternary expansion for the mu b around the 0, right? Just to truncate it to some water. For example, for this one, it's just as truncated to the 8th water, and this 2 plot is truncated to the 10th water. And we can compare the full result and the result of a ternary expansion. And from these comparisons, we can investigate the informations about the convergence radius of a ternary expansion. And here, this result, we select 2 value or temperature that is close to the critical temperatures. One is 155, and the other one is 162. And the curves that have a non-trivial oscillation behavior as a function mu b, that is the full result. The other 2 is just a ternary expansion. We can see it's when the mu b is about this value is about 1.5 or 1.2. the full result deviate from the result ternary expansions very significantly. So is that means that is that caused by, for example, the youngly aging singularities, but that will lead more research? And also we use the Baryon pad method resummation to improve the ternary expansion. Here, the Baryon's transformation is just given by this, right? And this is the capital F functions is given by this ternary expansion, and we can approximate this F functions by the pad approximate, and the water's pad functions is just determined by the waters of polynomial in the numerators and also denominator, just the LOM. And here we can see for the result for the pre-year, the lowest water, the full result, and the ternary expansion result, and the Baryon part approximate agreement, right? But with the increase of water, for example, the Chi2 and this Chi4, this is the full result. And this background is from the ternary expansion. And these two lines just correspond to the Baryon's pad approximation. And we can see it's also about 1.5. The full result deviate from the ternary and also the Potter's approximation. So we conclude that in our calculation, it indicates that the Baryon part approximate observed a lot better than the ternary expansion.
Kenji, 10 minutes, Wei-jie, 10 minutes left, right?
Oh, okay, thank you. Okay, with very careful determinations of the freeze-out curves, we can compare our calculated result with the experimental measurement. This is the students. This is to students. We can see is our calculations is a very in good agreement with the experimental measurement, except these two energy point, and because this is understandable. We think that in the lowest colliding energy, some effect, for example, the global conservations of the baryon number will play a role, but in our calculation, we have not taken into the baryon numbers global conservation, but in ours, and but for the moment, in ours ongoing project, these effects are taken into account, and this is the forced water, that is the kurtosis, forced waters, and we can see the long monotopic behavior is also obtained in our calculation. We also compare to the hyperwater 6 water one, and also in this plot, our theoretical result just as a green band is also compared with the new data of the R5 to R6 from the new experimental measurement. We can see for the 6 waters one is selective. It's agreement with our theoretical calculation, but there are still some deviation. And also here in this plot, I just to show the kurtosis in the freeze diagram, and the green line is just the freeze out line, and this blue line is selective. Correspond to the lectives of the kurtosis, and the red is correspond to the positive. And we can see it's with the decrease of the colliding energies, it's just moves toward to the regions of blue and then deviate from it. And that is when we decrease the energy, is just decrease and then increase. But I should remind that this is the region of increasing sharp crossover, lot of critical regions, right? And because for the moment, most the calculation have indicated that the regions of the critical region extremely small. And this part I have shown in the former slide. And beside this one, we also calculate the exponent beta. The betas as the functions of the temperature, the difference of temperature. That is the distance from the critical temperature. And we can see, so when it's very close to the critical temperature, the calculated result is the correct one for the Z2 in the 3D. And this black line is the calculated result from the conformal bootstrap. And it's usually believed that the conformal, the critical exponent is from the conformal bootstrap is very reliable. But when the temperature is away from the critical ones, we can see the critical exponent is not correct, right? So that means that the critical irradiance is very small, both in the temperature's directions or the time mass direction. Both are very smaller than 1 MeV. And also, so we in this slide, I just choose that in order to pin down the location of the critical endpoint, we need theoretical prediction. For example, from the latest calculation in the small and vanished baryon chemical potentials in these regions, and also in relative larger mu-B regions, we did the first principles of functional approach, for example, the FRG and the Dyson-Schwinger. We also lead the experimental measurement of fluctuation, for example, to the experiment to provide the fluctuations observable as the input, and the latest and the functional method provide the prediction of the location of a critical endpoint, which dependent on the fluctuation observable. Okay, in our calculation, we also found that interesting thing is that for the 2-point functions for the meson, for example, that is given by this equation, that is master, this is a wave function renormalization. We found the wave function renormalization at the temperature for different value of mu-B, and we can see when the mu-B is small, is positive, that is normal. But when the increase of the temperature with the mu-B, we can see in some region of temperature that is negative. So that is very interesting. So in this first diagram, we choose the regions where the wave function renormalization is negative. And recently, we also to find that the negative wave functions come from the Landau damping. In this plot, we choose this one. This is the contribution from the creation of annulations of a particle, and the black one is from the Landau damping. And we can see this is positive, but this is negative. So and the mu-B is large. This total Z is also large. And we also calculate the wave functions for the external, finite external momentums. And once more, we find that for the mu-B is very large. For example, the 500 MeV, and when the momentum is not very large, there is readings, the wave function renormalization are still negative. And the consequence of negative wave function renormalization, I think that in the seminars last week, Rob and Fabian have given a very nice talk. That is the negative wave function renormalization causes a mode behavior for the one particle spectrum, and also for the 2 particles correlation. And also, so we from the functional method, we can do the analytic continuation on the flow. That means we don't do on the data. So this analytic continuation is well defined. From that, we can calculate the spectral, that the calculated result given by these. And we can see that every structure corresponds of process. And with the increase of the temperature or baryon chemical potential, the spectrals of pion and the sigma becomes generated because there is formations of the chiral symmetry. Okay, I think I should stop here because they're limited time, and just to skip the real transform reason and just go directly to the conclusion. I think that's it will not affect this talk. And recent years have seen significant progress in the study of QCD free structure, statics and the dynamics properties QCD matter in heavy ions collision within FRG approach. And I think the most important take-home message from my talk that is the estimate for the location of a critical endpoint or the uncertainty of value physics from FRG and the Dyson Schwinger equation converge in a rather small regions at baryon chemical potential of about 600. And thank you very much for your attention.
Yeah, thank you very much, Wei-jie, for this very exhaustive overview on functional results of functional approaches to the phase structure of QCD. And I think I see already the first question. Claudia, if you want to.
Yes, hi. Thank you very much for this very nice talk. I had a question and a comment. So the comment is about the equation of state at finite mu. We have new results from Wuppertal Budapest, which go up to 3.5 mu b over t. So it would be very interesting to see how they compare to your, 3D plots for the equation of state.
Okay.
And for the question, I wanted to know about the kurtosis. If you can go back to the slide where you compare with the experiment and you see this non-monotonic behavior. I was just curious to see. So you have to assume a freeze-out curve there where you calculate. Yes, that one. Yes. So your green bands, which freeze-out curve have you picked? Are you sitting on top of the phase transition line?
Freeze-out curve, right?
Yeah.
Okay, I will choose it. I have this just a moment.
Yeah.
Sorry. Yeah, this way. In fact, we choose the freeze-out. We have three freeze-out curve. The first one is just from this paper. This is from here, and this is quite used often. And the other two is from the stars data or freeze-out data. That is the 6. I think that is the several point. And we argue that we use the best one because we think the best one. I think that these 2 point is I think there's maybe some crossings here because it's go up and then down, and so the curvatures should be positive, right? And so we compare very careful for these 3 different freeze-out curves, and we also show the result for the different the different freeze curve, and we can see for this curve is also it's always the non-monotonic behavior is always there.
Okay. So yes, because I was wondering if you go away from the phase transition, because from your plot of the kurtosis, it looked like the negative band is relatively narrow. So I was wondering how far away you can go. Let's say the freeze out is not right on top of the transition line. Is that this deeper, robust feature or not?
Yeah.
But okay. Thank you.
Okay, thank you. Are there?
Yan?
I think there are some others. Hello?
Hello?
Yeah, I don't know where's Yang, but anyway, maybe Jimin, you go ahead.
Oh, sorry.
Okay,
I said something, but I was muted. I said exactly, Jimin, go ahead. Coach Jimin, go ahead.
Okay, thank you. Wei-jie, thank you for the so many impressive new results. My
Thank
question
you.
is first, let me comment on what Claudia asked and you replied. Those freeze-out curves, they are from chemical freeze-out. But
Yeah.
expand the measure, there's kinetic freeze-out. If I remember correctly, there's one paper by Asakawa, Yuki Asakawa, another paper by Jan Steinheimer. They checked all those fluctuations of the kinetic freeze, chemical freeze-out, they change after hadronic evolution at kinetic freeze-out. Therefore, one has to be very cautious to compare the theoretic calculations based on chemical freeze-out to compare with measurement. Just a comment.
Okay.
If you put all your fluctuations into hadronic after burnout, they will be modified by the hadronic evolution. Okay, because the rapidity will be modified, the PT will be modified, so they changed. Right. But that's one comment. Yeah, the other, I have one short questions. I'm interested, find that Landau damping, that's very interesting. You get a negative, the Z, the negative. Is that a universal properties of Landau damping or just specific for QCD? I can look at the electron, many electron systems and other nuclear metal systems. They also have Landau damping. Do they also give negative Z wave function renormalization or just for QCD?
I think maybe it's not constrained to just the QCD. Maybe it also come from other theory, or maybe it's QED, because the Landau damping is quite general, right?
Yeah, but the sign may be sometimes positive, sometimes negative, depending on the system. Am I right?
Okay. Okay. We will investigate more carefully there.
Okay.
Thank you for the suggestion.
Jochen, want to go ahead?
Yeah, thanks very much for the nice talk. On various slides, you showed some theoretical uncertainty bands.
You mean for which observable?
Several of them.
One? This one?
Yeah. Yeah, for instance, let's, for instance, maybe go a little bit later for the cumulants.
Cumulant. Oh, okay. This one.
Yeah, for instance, in some of them, you assign theoretical uncertainties to the FRG calculations. How do you determine these?
Okay, I will show you in the backup slide. Just for this. Just for a moment. To look for. Okay. Okay. In our calculation, we use the two flavors result to match the 2+1 flavors. So we do our scale matching, but this scale matching is guaranteed. For example, in our QCD's calculation, we can say we can adjust the scales, the matching, the two flavors and the 2+1 flavors in good agreement. So in our calculation for the fluctuations, we perform the calculation to the two flavor, but to include the strange quark effect to take the scale matchings, we use it like this, right? But these arrows in our calculation, the arrows come from the coefficient of for this matching. Just like the.
Thank you.
Oh, you're welcome.
So Nushu, you're the next one.
Yeah, hi, Wei-jie. Thank you for the
Hi.
very nice talk.
Thank
I
you.
have a question about has to do with experimental observation. Can you go to a slide of use the slides title, because I don't have slides number, update critical point.
Update. Okay.
Update, yeah, critical point. So you show the two temperature, one from FRG, one from Dyson Schwinger equation.
Yeah.
My question is, so this prediction, this is your prediction, right? And
but I said that this is not our prediction. This is just an estimate, because that is beyond our very reliability regions. This region is given by this blue region. So
okay,
that is
okay.
Yeah.
And you say you estimate. Then based on what you estimate? Why not, for example, 700 μb MeV for μb?
But no. This is obtained from our theoretical calculation. But we say that this estimate, because that our theoretical calculations, the reliability of our theoretical calculation, the error is not here. Because for example, in FRG's calculation, some degrees of freedom related to the densities of fluctuation, maybe that play a important role. And for example, at large μb, the Dirac effect maybe will play a role. That will maybe affect the location of critical endpoint. So that is what we said. It's obtained from our calculation. So.
Okay. So then, what is the consequences? You also have a slide on the high order covenant ratios, right? And what you did not really go to 600 MeV, for example, not this one. I think the energy dependent.
Okay.
You stopped at around 400 MeV. Not this one.
Yeah.
This
this
green band, yeah, green band.
Green band.
No, not this slide. You have a slide. Yes, this one. For example, you stopped at 7.7 GeV, where μb is about 400.
400.
Yeah, 400 MeV. So 600 would be go to left. What would be your prediction for these observations?
You can see our base, the largest μb in our calculation is here. It's here, and in fact, for the very large μb, the calculation is difficult. It's difficult, and for this compare with the experimental result, we have not done yet. We have not done yet for lower or higher μb, but that will be due. That will be.
Okay, thank you.
Oh, you're welcome.
Maybe I add to this. I mean, the computation we have used there is less advanced than the codes we use for the phase structure. We are at the moment doing this also for higher densities with the QCD code, and then there will be results. So we stopped here because there our QCD assisted model really loses credibility, and you see this with the large error bar section.
So
okay, you have to stay tuned. I'm sorry to interrupt.
Oh, great. No problem. Thank you. Now, if I may follow up a little bit, for such calculations in terms of thermodynamics, are they ground canonical or is a canonical? Do we have a conservation?
That is grand canonical. That is grand canonical.
Oh, ground canonical for large μb is a questionable, right?
Yeah, right. Yes. As I have mentioned in here, for there is a significant different discrepancies between the theoretical calculation and the experimental result. And we are also doing in our ongoing project. We would like to take the global baryon numbers conservation into account.
Thank you.
You're welcome.
So Jürgen?
Yeah, thank you for the nice presentation. I was wondering if you could apply your results, which you have done for the QCD phase diagram for heavy ion collisions, for the QCD phase diagram for the early universe. You know, I mean, the early universe also goes through the QCD phase transition, but it's actually not really known where, because one can tune the lepton chemical potential, which in your case would be the charge chemical potential. So my question is, could you follow isotropes in a diagram where you conserve for a given charge and baryon number through the QCD phase diagram for these two chemical potentials, mu baryon and mu charge?
That means you take, for example, in heavy ions, you should take into account, for example, the strangeness neutrality, and for example, the ratios between the charge and the baryon number, that is a fixed value. That means we should implement the strange chemical potential or the charge chemical potential. We have for the QCD calculation, we have not included, but that is doable. And indeed, in our effective calculations for the correlation with fermions and ions, we have to take this into account.
You have to fix the strangeness chemical potential to be equal to the down quark chemical potential, right? There's weak equilibrium, and then I think you can do this. There was a recent work by Fei Gao and Isabel Oldengott in the Schwinger-Keldysh approach. So they did this actually.
Thank you.
We know Fei is part of our collaboration.
I know,
Okay, Thomas?
Hi, thanks a lot. There's an old question whether the axial anomaly is effectively restored near TC, and whether that somehow affects the expected, O4 universality of the chiral transition. Is that something you can study, or is that incorporated in some way?
Sorry, can you repeat your question?
There's an old question as to the fate of the axial anomaly at TC, and whether an effective restoration somehow affects, O4 universality of the chiral transition.
Yeah, that is the actual for the anomaly, actual anomalies, I think for the moment we have not taken into account, but I think I think I have not. I have
maybe
no
I
idea
may
about
add to
that.
it, because there is something in progress, and Wei-jie is even involved. There are some works also by Jens Braun. So in a way, at the moment, we have taken into account maximal anomalous symmetry breaking, but we are at the moment studying an approximation which is totally unbiased in this direction, and then we can study this phenomenon. It's a bit a technical problem, because in order to get really our hands on the prefactor of the respective terms, we have to really start at very large scales. So we are not talking about starting at 20 GeV or 50, which we are doing at the moment. We have to start at 100 GeV or more for technical reasons. And that is numerically challenging. But we also hope that within the next 1 or 2 years, we can make a statement there.
But so effectively, what do you assume right now? That it's always broken or always restored?
It's always broken.
Yeah.
So the combination of terms we take into account is a maximally breaking anomaly.
So you assume that there's just no degrees of freedom in that channel that are allowed to fluctuate somehow?
We at the moment don't take into account additionally separately the TOF determinant. So you see that there are always combinations of the TOF determinants with other chiral channels, and we take the maximally breaking one into account.
But I think that is related to the four-quark couplings, right? To
yes,
the channels,
I mean,
but so your four-quark coupling is symmetric or asymmetric?
It's all symmetric.
So you assume a kind of maximal anomaly, don't you? That there's just
absolutely.
Yeah.
Yes.
Yeah. I mean, even though there's no mechanism for it, you just assume that somehow it's so big that there's just nothing fluctuating in that channel.
There is an investigation by Jens Braun, myself and collaborators, where we test the effect of detuning this.
Okay.
And the effect on. Sorry?
Yeah, thanks.
Yeah. Coach Jimmy. So your hand is up. You want to ask a question?
Sorry, I forgot to unmute. So before I ask my question, I just make a short comments. You mentioned that the critical point is estimate because you haven't include diquark correlations. In other words, you don't have a nucleon in your system. You only have a pi and meson. Therefore, to apply that to neutron star, it's probably premature at this time for you to do it, right? You have no nucleons. That you first have to have a nucleonic degrees of freedom in order to extend it to neutron star. So that's my comment. My question is, I think I asked Jan Lowski before one time. I couldn't remember exactly how he answered me. I asked those lattice people, what's the quark number density versus the gluon density at TC? And they cannot answer me that questions. Can you answer that questions within your approach? At TC, what is the system, the quark density versus the gluon density? I think you can calculate that way, right? In your approach.
I think that because in our calculation, we calculate the flow. So the flow received contribution from the quark, and also from the quark, and also from the gluon. But
you also have a spectral function. I remember you also have a spectral function for quarks and gluons, right? As a function of temperature.
Yeah, that can be calculated.
Once you have a spectral function, you can use it to calculate the density, the number density.
Be aware of
the entropy as well.
The baryon densities we can calculate, but for the energy densities from we can separate the different contribution, but can we see that is just come from? Can we separate?
I vaguely remember your question, and I think I now tell you the same as before. If you define me what a gluon is, I'm happy to compute it. We have a gluon spectral function, but keep in mind we are using a gauge fixed approach. And that is a gluon in the Landau gauge. So I don't want to get carried away there and say this is a physical gluon. Okay.
Okay, I got you. So depending on which gauge you calculate.
Landau gauge.
Landau gauge. Yeah.
Okay. I see. But you do know, if you know the quark, you said no problems. So you know the quark number. You also know total energy density. Now from a quark number, you can calculate the quark energy density. Then you can extract the gluon contribution to the energy density. From there, one can get some idea what's the gluon number roughly, right? So my point is quark dominated, the gluon dominated. The point is.
That is possible, but keep in mind also these loops we compute are gauge fixed. But I mean, if you want to have this, we can give it.
Okay. All right. So I still don't know.
And
But that's
I want to
dynamic,
make a
isn't it?
comment concerning the diequarks. First of all, I mean, Jens Braun and his group have done a lot there, also at large densities for the astrophysical question, so nuclear astrophysics. And also one has to distinguish between diequarks as external objects, of course they are not asymptotic states, and off-shell diequarks. So we don't have explicit diequarks hanging around. That does not mean that diequarks are not in the approximation. But what I agree is, if you are talking about astrophysical questions, you should have them explicitly in your effective action.
Thank you. Yeah, the reason I'm asking the quark and gluon degrees of freedom in QTP, because we know now a lot of the property of QTP is transport coefficients and the thermal conductivity, viscosity, and so on and so forth. But we still have no idea what's the dynamic degrees of freedom in QTP. There's something, although it's strongly coupled, right? So, but still, they should have some, must be still play a role. What's degrees of freedom? How important is quark versus the gluons? Of gluon
there is an investigation by Jens Braun and his group where they look at the relevance of the different channels of the four Fermi interactions. And for quite a while, it's the pion. I mean, if you look at it as a function of density or chemical potential. And for quite a while, it's only the scalar, pseudo-scalar channel, which is important. So you can switch off the rest and they don't play a role. And then there's a very rapid transition to being diquark dominated. There again, you can switch off the rest and they don't play a role.
I see, okay.
It's a case study and it's very difficult to translate this into, I mean, physical chemical potential. And it informed our estimate of mu B over T is 4, actually. So, Wei-jie Fu.
Hi, Wei-jie. Hi. Thank you for the nice talk. Hi. I have questions. In your FRG calculation, can you have you considered the final size effect? Because in Finite collisions, the plot, the fiber you created is finite volume.
This can be investigated in principle. And for example, for the finite volumes effect, we can use different. For example, the cutoff for the momentum, right? There is some for the momentum we can. And also we can use the boundary condition, and we can calculate. We can investigate in our calculation.
Right, good. Also for the high Baryon density cases, Luke asked a question. So beside the rich structure in high density, because for example, diquark condensations and inhomogeneous phases. So I don't know what's the update. So you know, we had discussed it several years ago about the bending back behavior at high density. High density, and we tried it by including the raw mass, but it doesn't have sense. Is there any progress in this direction?
That we have not do that for that, because that is take place the bent band.
Bending back.
That is take place at very high densities. We have not to investigate in this region, but that is another story. That's for the effective theory. That is founded how many years ago? Maybe 20 years ago, right? And
for the effective theory.
But I think Young and his collaborators, his students have made some progress here, right?
We are using now discontinuous Galerkin methods to get our hands on the potential in this regime, because this regime is also potentially, there are potentially shocks in the flow equation, which you have to take into account. And this is why we use this more elaborated methods. And I also hope that there will be results out soon.
Okay, thank you.
But it's a very delicate question, because it's a combination. First of all, you need to get your models under control, and then you have to work this into the QCD code to have a final answer.
You have to control the fluctuations too much or what? Right.
Yes.
Yeah.
Okay, thank you.
And I remember our discussions, which was actually in 1919, the last workshop I attended in Wuhan. Okay.
Okay.
So I think we are also, I mean, we are pitch perfect. It's 3:15 in Germany.
Yeah.
And so let's thank Wei-jie again for this nice talk.
Thank you.
And I don't know whether there are further announcements, so I hand it over to the hosts if they want to have some final announcements.
Thank you, Wei-jie. Thank you. Yeah, very nice presentation. And
You're welcome. Thank you.
Thank you. I think it's now the ending of this presentation, and thank you for the participants.
See you next
Thank
week.
you all. Yeah. Bye bye.
Bye bye.